Hi everyone, welcome back. In this video, what I'm going to do is talk about electrostatics. So at this point in our year, in terms of physics, we're actually going to shift gears quite a bit. And as I'll describe in the lecture, I'll talk about what we talked about before and how it's different in terms of what we're doing now. And as you can see, we're going to talk about charge. And particularly in this lecture, we'll talk about properties of charge. Then I'll talk about interactions of charge. So we'll talk about charging objects and how objects interact with each other. So how, for example, objects can be attracted or repelled. And then the third video of this series will be Coulomb's law. So that is all about calculating the force between two objects that attract and repel. So, like I said, those are the three video series involving the introduction to electrostatics. So, as I said in this video, here we go. I'll talk about the fundamental properties of charge, identify the characteristics of charge, define what it means to be quantized, and then we'll do some calculations at the end of the lecture here on net charge and number of charges. So, for the first part of physics, we deal with what is called mechanics. Let me just put everything up here so I can talk about everything at once. There we go. Okay, so like I said, we talked about mechanics, and I've never really kind of mentioned this, but essentially what I'm talking about in terms of mechanics is mass. But, like I said, I've never really specified it. So we talked about linear motion, we talked about how Newton's laws explain why things move, and we're all looking at the interaction of mass. Now, I actually didn't talk or go over gravitational force specifically, or gravity. But solely based on mass, objects can attract each other through this force called gravitational force. It's why we're on the Earth right now. It's why all the things on my table stay on the table. It's why I'm sitting down in this chair. It's why the Earth is rotating or revolving around the sun, and it's why the sun is revolving around our solar system. Well, it is in our universe, etc. You get the point. I was trying to go higher and higher. But the point is that it's all based on the object's mass. So things can interact through mass. And we call that mechanics. And if this were a traditional physics course, and I'm talking about Physics 101, we kind of do in 101, we kind of do everything together. But typically physics is broken up into two courses: mechanics, the study of mass and motion. And then part two, it's the study of charge. So let's see, we're a little more than halfway done. So we're getting a small piece of this section of physics. But it's the interaction of charge. And at some point in your careers, I know you learned about positive and negative charges, whether it's through physics before or chemistry or physical science. And you know that like charges repel each other and unlike charges attract each other. So I'm assuming you have that background. And if you don't, you'll get it. But it turns out that when things interact with charge, they actually have very, very, very similar, similar interactions to that of mass. So just like there's gravitational force between two masses, there's going to be electric force between two charges. So we're going to actually see some similarities in this, and we'll be able to calculate these things, such as electric force. We're also going to look at some of the other features of charge. Charge is actually pretty amazing. And okay, I'm almost there. And you notice I didn't really specify, but this is one of the fundamental properties of matter. So in other words, when the universe was created, it made matter, and the matter had, it actually has three, but we won't worry about spin, but it came with some properties. For example, its mass, how much stuff it's made out of. And its mass is kind of based on the some atomic particles. So we could break it down even more than I am going to share with you in this lecture. But we have matter, and it has mass, and we have matter and it has charge. So charge right now as positives and negatives. Neutrons have no charge. There's a plethora of other types of subatomic particles I'm not going to talk about, but they also have mass and charge. So it's all related in that sense. And as you can see in these images, gravity makes what is called a gravitational field. So in other words, if you're really heavy enough, you can actually distort the space around you, and you actually call what is gravity is an attractive force. And that's really interesting about gravity, that it only attracts and never repels. So here's an image of Earth in this, making a gravitational field, right? The Earth is heavy, so it distorts the space around it, causing things to be attracted to it, like that looks like a satellite there. Well, we have very similar things with the electric field. So charges actually alter the space around them, so that if another charge comes into contact, it interacts. So mass interacts with mass here, and charges interact with charges here. In other words, the mass is not going to be attracted to a charge solely based on mass and charge. Mass and mass attract, charge and charge attract, but not charge and mass. So that's why they're two separate things. And just like I said with gravitational field, your electric field is governed by charges here. So we're not going to actually, in this course, we won't go into the electric field properties, although it's really cool stuff. Everything's cool stuff in physics. You should know that by now. But like I said, we won't go through this. I will talk about what charges can do, because I think a lot of times when you go and have a physics course, you learn about all this stuff, but maybe not why or what's the significance and all that fun stuff. So I just wanted to give you some significance about charges, because they're actually pretty cool. I didn't bring any props with me, so let me grab this case. Let's pretend. Usually I have something with me, and it's really sad I can't do a lot of these demos for you in class. But imagine you have a stationary charge. This is just an electron. Just assume it's an electron. Well, charges that stay still make electric fields, and they're responsible for things for that static electricity. So in other words, if you if you're wearing a sweater and you pull it off, and all of a sudden your hair starts going off in all different directions, that's caused by electrostatics. In fact, our first lesson will talk all about that, why your hair becomes charged, all that fun stuff. That's electrostatics. It gives you that static electricity stuff. You take a charge and now you start to move it, and you immediately make this thing called a magnetic field, which is interesting because you're saying, okay, I know my my magnets in the refrigerator don't move, which is true. But inside there's there's atomic properties that have movement of charge, or these things called spin, that create this net magnetic pole, or domain it's actually called. And what we have then is this thing called magnetism. So when you have moving charges, you make magnetism. It's pretty cool. Another effect of moving charge is current. This is what we will talk about, is circuits. If I give the electron some energy from a voltage source, we can get them to move around. And quite technically, these are related. Currents do create magnetic fields. So anytime you're near, a wire, for example, I'm looking at my computer wire right here, that is making a magnetic field. And in fact, if you really want to go crazy, you can find a compass, and you'll find the compass does deflect due to that. Now, magnetic fields are generally weak. We're in one all the time from Earth. In fact, some of your soup cans in your kitchen are probably magnetized because of it. If you have a can that you just haven't moved in, years, and take a compass to it, you'll find that's also magnetized. Another fun fact for you. But anyway, just the property of charge makes electrostatics, makes magnetism in circuits. This is all based on your charge here, whether it's stationary and moving. And then you get this last effect, oscillating charges. So what happens is if you take your charge and you move it up and down like this, you get both electric field and magnetic fields, because it stops and you get electric field, it moves, it gets a magnetic field, stops, electric field, etc. It goes back and forth, hence the word electromagnetic wave. Ever catch that? Well, we make the spectrum, so you might be familiar with this too, with the radio, microwave, infrared, light, UV, X-ray, gamma rays. So all the electromagnetic spectrum right here for you. So I put light. And of course, light is incredibly important for not only our seeing, but for communications and sound waves. So we talk about waves in this topic too. Mostly because of light, but there's also these things called mechanical waves. Notice I say mechanical waves are based on mass, matter. So those are different than electromagnetic waves. So we'll do both in this course, Physics 101. We'll talk about mechanical and magnetic waves, electromagnetic waves with that. So the charges as a whole are very important to study. It's very important to know what they do. And I know all of you are not physics majors, but I hope you have, even just this one lesson, I hope you have an appreciation for what charges do in our everyday life. Okay. So, like I said, again, a little asterisk there because there's actually other fundamental properties, but we're going to ignore those. But the two fundamental properties of matter we'll talk about are mass and charge. You don't have to memorize these at any point. I'll give you these values for you, but it's good to be aware of the following things. First of all, the electron is smaller than the proton, as you can see there. And another really important feature is that the charge of electron and proton are actually the same value. In fact, we need that to get electrically neutral things. They need to cancel, so that's important. But masses don't cancel, and they don't have to cancel because mass is always attractive anyway. But we can get electrically neutral things from this very interesting property. Now, something else here is that I put the neutron here because we're familiar with it, but honestly, the neutron's going to take a seat for this entire class because it's not important at this point. Neutrons are important for other things because the fact that they have zero charge, but like I said, we're not going to talk about them. And they're very similar mass, to the proton. It's slightly bigger, but not by much. But the mass of the electron is pretty small, as you can see here, a very small element. Now, the symbol for charge I will use is Q. That's pretty standard symbol for charge. What happens is that you might see online sources, if you're doing so, use the E for the electron as a charge. But like I said, I personally like to use the Q symbol. And the units of charge are coulombs. So just like mass has kilograms, charge has coulombs. And as you can see here, let me take a quick step back, is that this is such a small number, and generally charges are small values. So even if I charge up a balloon, it's still a very small value. So we use the metric system to kind of help us with that. So be familiar with these terms, milli, micro, and nano, and notice it goes in orders of 3. Milli is -3, micro is -6, and this is -9. You can put this on your equation sheet. This is an accepted thing to do. You don't, again, need to memorize this, but you do need to recognize these symbols and when to use them. And I'll go over that too. This was from the AP Constants and Conversions page. I just always liked it because it had everything in one spot. So I put it here for you. You can put this on an equation sheet if you want. And this, of course, very helpful. Although I typically only use these three. Like I said, you might see some things in the femto and the pico and the giga in other places. So just a reference page for you. So charge was first measured by this very famous experiment called the milk and oil drop experiment. I happened to do this simulation in my high school, and I don't know why. I've done a lot of labs, so I always remember this one. Because essentially what you're going to do is, in the lab, what you did is you had a little oil drop, and the force down from gravity is countered by the electric force up. And if you add enough electric force, you can get it to balance gravity. So then we could say the force of gravity is equal to the electric force. And now we can get this thing called the charge to mass ratio, which is actually mass to charge would be the inverse, but that's okay. Either way, they were able to figure out the charge based on the mass, which is a really, really clever way of doing it. And they were able to get a really high order of accuracy doing it. So I'm very impressed with this experiment. But that's how the unit of 1.6 times 10 to the -19 came into play. It was done by this oil drop experiment. Charge is charge is quantized, which means it's a fixed amount. It means that no matter what you do to it, it's not going to change its value. Just like a quarter. If I took a quarter, there's nothing I could do to that quarter to change that it's 25 cents. Even if I did cut it in half, the quarter is no longer, useful. You can't use it anymore because now you destroyed the quarter. Kind of the same idea here. the electron is always 1.6 to negative 19. You can't do anything to destroy it, which means that you can only get integer multiples of one another. It's a very big word to say that you can't change the value. So if you have 2 electrons, they're both going to be the same value, 1.6 to the negative 19th. You can't get a half electron or a quarter of an electron, 1.234 things electron, so that will not exist. Now I do have to make a side note with this because this does confuse people. So let me just quickly draw on this because it's, like I said, it's common that it confuses people. Do I have my thing open? I thought I did. Thought I had it open. Must have closed. Okay, sorry about that. Come to here, go to here. Okay, it's opening up now. We'll give it a second to open up. There we go. Gotta change the color. Okay, so the point I wanted to make here was that sometimes you might get something like this. Say you have 1.53 times 10 to the 8th electrons. Say you have just a lot of electrons. This value is acceptable because the following. This number means 1.53 times 10 to the 8th. So it's 153 and then 8. So 1, 2, 3, 4, 5, 6, 7, 8 electrons. Notice that I don't have decimals here. That this is okay. What's not okay if I did 1.53 electrons. That's wrong because I don't have a times 10 factor here. So just note that. I know I get a lot of questions regarding that. How can you have this here when you told me it was quantized? So that's what it means. Okay, so you know this, but I'm going to say it just in case. Protons are positive, electrons are negative, and neutrons have no charge. And that's enough on that. Charge comes from atoms, so if you're wondering when we charge things where they come from. But generally atoms are electrically neutral. I put a star there because some cases they're not, but in most cases they are, which means they have an even number of protons and electrons. So just to be very clear here, because I know that I'm just going to get rid of that dash because we're not too far here. Let's go back, sorry. Okay, sorry about that. Okay, so where do charges come from? Well, if you want to know where charges come from, I mean, technically there are some that are floating around in space, but in terms of everyday, they come from the atoms within objects. So 99.9999% of them are all electrically neutral, which means that there is an even number of protons and electrons. So if you take a look here, if you count, there's 1, 2 electrons, 1, 2 protons, we ignore the neutrons. So electrically neutral, and it means there's no interaction. So in other words, you know, like my Moby right here, when I touch it, I don't feel an attraction or repulsion from it. I mean, I'm electrically neutral, it's electrically neutral, nothing happens. So that's kind of what this means. So when do you get an interaction, right? That comes from charged objects. So if we kind of look back at this example again, it's going to be from the removal or the addition of electrons. If you notice the structure of the atom, the electrons are on the outside, which are easily moved. You actually, and notice that, first of all, a couple things. The protons are never moved. They're stuck in the atom with this strong force. That's the official physics name for it. It's actually amazingly strong because technically these don't want to be next to each other, right? 2 protons want to be far away, but the strong force keeps them together. So I'll tell you, no act of charging an object will remove these. And in fact, if you do, you release a ton of energy. And that's, of course, not what happens when you take a balloon and you rub it, right? You don't release a ton of energy when that happens. So it's all going to come from the electrons, whether you add more or remove more. So it's an imbalance of charge that causes objects that are charged. And notice that this object, even though it's on this slide, is not charged, right? Because we have the same number of electrons and protons here. And again, another word for uncharged is neutralized. So I hope you noticed that term that I used here. Okay, so we're going to go ahead and calculate these things called net charge. So the net charge is just how much charge you have in coulombs. So it's looking for the coulomb value of charges. So to do that, what we're going to do is we're going to figure out how much excess charge there is. Are there extra electrons to make it negative or extra protons to make it positive? And then for every proton electron that are together, one cancels out another. And I'll show you what I mean by that. So first we got to determine what the excess charge is, and then we're going to take those total number of charges and multiply it by Q. So this is, again, the charge value for each are the same, but we model, the words model, electrons with negative. Are they floating in space with a negative sign? Nope. We use it to mathematically model what's going on because the electron is the opposite of a proton. So notice the negative term for that. So here's a quick example of calculating net charge. So let me just grab my marker right here. So I try to do a visual example. Say you have a pile of electrons and protons just sitting there. Normally this won't happen, but use your imagination. So what's the net charge of all of this? Net charge Q. Well, this electron will cancel out this proton because they have the same charge. Notice if I add them together, they would get 0. And that's true for every proton to electron. So there you go. You don't have to do exactly what I did. You could say 3 minus 3 here. And notice I'm left over with 3. So my excess charge is 3 electrons. Notice what I said there. So this is my excess charge. Now to calculate my net charge, I'm going to take the total number of excess charges and multiply it by either the proton or the electron value. So since we're dealing with electrons, we go electron. So the net charge, is equal to 3 electrons times the charge of an electron, negative 1.6 times 10 to the negative 19 coulombs, like that. So I'll take my calculator. Now, when I do it on my calculator, just like using any sort of large value, I'm going to do 3 times 1.6. I'm going to use the capital E button on my calculator. So actually, just a little fun fact, this comes from using the button. You have to press second, and the button actually looks like this. It's actually the comma. This is a TI-84, but there's a double E right here. This is for doing large numbers like exponent. E here means times 10 to the whatever. So notice I use that instead of writing that because in the calculator, especially in my TI-84, this is bound to give me the correct answer and not follow the order of operations and all that fun stuff. If you do 1.9 times 10 raised to negative 19th, your answer is off by 1 factor. So let me just do it first the way I like to do it. 1.6 e to negative, 3 times 1.6 e to negative 19. Oh boy, this is what happens. Hold on. All right. That's the wrong button, sorry. E to the negative 19. Okay. The answer is 4.8 times 10 to negative 19 coulombs. That's my net charge of the pile of charges there. Now, I want to show you something. I know you can't see my calculator. Can you see my calculator? No. If you do this, 3 times 1.6 times 10, and you do that caret to the negative 19, this is the answer you get. And type it in just like that, as you might type it in. Notice that this answers this. Sorry, this should be negative because of the electron nature of it. Notice that it's off. Oh, okay. What did I do? It isn't off. It's actually right. Okay, no, that worked out. Never mind. I know sometimes if you don't do, sometimes if this, so my calculator picked it up, so that's good. It calculated the right thing. Just be careful about this. I know some calculators that don't do it correctly. So that's okay. As long as your answer is matching mine, I don't care how you find it. But I guess it didn't prove the point that I wanted to. Oh well. But anyway, the most important thing, that's the net charge of the situation. So some other things, we model charges with signs. Protons are positive, electrons are negative. So in other words, if I have excess protons, then that's going to give you a positive charge. Or if I said deficit of electrons, that means I have less or lack of electrons. So that also means positive. So notice that these things mean different, can have different meanings, right? Excess electrons is negative, but deficit protons makes it negative. So just be careful with the wording. I know in the homework you have different wordings for this. So there's many different approaches for this. You know, I have these in the notes, but I also have one for you. Also have number 1 for you. But if you have 15 electrons and I want to find the net charge, it's going to be 15 times the charge of 1 electron. (15 times 1.6 e to negative 19). I keep doing that. E to negative 19. There we go. 2.4 times 10 to negative 18 coulombs right there. And then this will also be negative because of the electron nature. So that's the net charge there. Some other common mistakes is sometimes people will do this, negative 2.4 coulombs. And they forget to read the exponent on their calculator. So just careful with that, okay? I probably will see 2 to 3 cases of this in your next quiz. So just be aware of that. There is always an exponent there. And then notice that this would actually be the same answer for 1, except it would be positive for protons. And then you do the similar nature, so you would have to subtract this first for part 3. 25 electrons minus 13 protons gives me a leftover of 12 electrons, and then I would go ahead and calculate that out. Negative 1.292 times 10 negative 18 coulombs, like that. And there you have it. So that's net charge. Hopefully those don't seem too bad for you. Determine the type and quantity of charge. So notice the wording, right? Deficit electrons means positive, right? Because I have less electrons than protons, so this is going to be positive. And I have extra electrons, so this is going to be negative. So that's fun. And then to find, I have that many electrons times 1.6 times 10 to negative 19 coulombs of charge. Okay, and when you do that, you get 4.0 times 10 to 11 coulombs of charge. And this one would be 5 times 10 to the 12 electrons times negative 1.6 and 19 coulombs. 8 times 10 to the 7th, -7 coulombs of negative charge for the electron. And there you have it. You don't need to put the positive sign there, but you do need to put negative signs in to get them correct on your quiz. You'll definitely see these on your quiz. Another quick side note is you could program Q into your calculator, or so in other words, what I can do is, since I'm using this number quite a bit, I could program this into my calculator. So the way I could do that, if you have a TI-80 whatever kind of calculator, what I'm going to do is first write the number 1.6. I'm going to use the E button, -19. So I'm going to write that in right now. And then what I'm going to do is press the store button, which is actually this one here. It looks like that. STO, it says, STO, and it's right above the on button. That means you're going to store a value. So when you do that, I'm going to press that right now, you get a teeny tiny little arrow. And then next you're going to set the value to some letter. So I'm going to do alpha Q because, you know, that's the letter I want to use. And Q is the number 9 because I have written above. Yeah, this is the alpha button. So when I do alpha Q, I get the Q that pops up. And then I'm going to press enter. Oops, I'm not supposed to say enter, that's not going to fit well. Spelled enter wrong, oh boy. Enter, there we go. And when I do, it's actually just going to give me the value back. So you could test it. So what I'm going to do is do 15 times Q. So 15 times second Q. Oh, sorry, alpha Q. It has to be alpha Q, not second. So it gives me 2.4 times 10 to the -18. And I'm just going to verify that by just making sure this matches this number. Oh, I keep doing that. And it does. Q works. So instead of writing that number over and over and over again, I'm going to just type in Q in my calculator. A fun little trick for you. In fact, I've now programmed it and I'm never going to use this number again. I'm just going to use Q. Okay, so the last thing we could do in this is go backwards. We're going to determine how many charges make up that total charge. So, you know, for example, let's say you have this, you know, like one of those globes. I used to have one, it's pretty cool. I actually don't know how many electrons are in there or how much charge. I just made it up, just fun fact. But how many charges in this plasma globe, how many charges are in this plasma globe if the net charge is that? So what I'm going to do is determine the number of charges, which I have here. And then you got to determine if it's positive or negative, so you use the right value. I just put charges, so we're going to go ahead and just make it positive just to make things easier. So essentially what I'm going to do is take the net charge and divide by Q. So 3 times 10 is -6 coulombs of positive charge, why not? Divided by the charge of 1 positive charge. So I'm going to do 3e to the -6 divided by Q, because I can do that. And when I do, I get 1.875 times 10 to the 13th protons, because I said positive. Now remember, this number is okay as a decimal because this is part of a big number. So 13 would be 1, 8, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's how many protons are in that globe. It's probably wrong, but whatever. That's how you do this. So so you take your number of charges and you divide it, your net charge, and you divide it by Q. Now this is going to be a positive number because you're calculating a number of charges. This always has to be positive. If you get a negative number, you don't usually count your numbers 1, -1, -2, -3. You always go 1, 2, 3, 4, all that. So that's making sure that your signs are matching. So let's look at a lightning bolt. This is an actual number. So if I want to find the number of electrons, notice that this is negative, so this is electrons. -10 coulombs of charge times -1.6 times 10 to -19 coulombs of charge, because it is in fact electron. So alpha Q, like I said, I'm never using the other thing again. 6.25 times 10 to the 19th electron. So, as you might imagine, the unit is electrons because you're counting. A lot of electrons in a lightning bolt. I think that makes a ton of sense. So that works out good. Ooh, now we have something we need to be aware of is this micro charge. So if I have something like this, I actually have to take an extra step. If it's not in coulombs, you have to convert out, or convert out of metric. So I know that's micro, so -6.7 microcoulombs times for every 1 microcoulomb, and this is in the front of the slides, so the beginning of the slides, it's 1 times 10 to -6 coulombs. I have to do this step first. Do the conversion factor. Now I am going to 100% put this on your quiz, because I want you to be able to convert things. Mess something up here. Hold on. Delete. 6.7 times 10 to the -6. Okay, sorry. 6.7 times 10 to the -6 coulombs of charge. So once I convert, step 1 is convert. Now I can actually go ahead and do the number of charges. Now notice that when I do the number of charges, this is negative, that stays negative. That this coulomb, they have to cancel. So it has to be in coulombs. Divided by Q. So times 10 to the 13, this is in electrons. Because it says electrons, the units are electrons, I will ask that on your quiz. Is it protons or electrons? So make sure you have this understanding as well. And notice that these cancel to make it a positive number, again, because we're counting. Some helpful tips. So in other words, when you're calculating net charge, you must multiply by Q. When you're finding number of charges, you divide by Q. Unfortunately, people get confused by this because it's so similar. You multiply and divide by one of them. So just be aware which one you're doing and be careful. Number one mistake is people mixing these up. Not messing it up, mixing them up. And another way to kind of think about things is, I use the money analogy. Charges are quantized, quarters are quantized, sorry. In other words, it's always 25 cents. Like I said before, you can't take a quarter and just break it in half and try to change the value. You just ruin the quarter. And if you want to have the net money, if I say I have 4 quarters, how much money? I do 25 cents times 4. That's net money, right? Or I could do the opposite. If I have $2, how many quarters do I have? Well, I divide by a quarter, right? And when I do that, I get 8. So think of it that way, because that's exactly what you're doing when you come to finding net charge and number of charges. So the focus of this part of the course will be on the fundamental property of charge. Charges are quantized, which means this value never changes. Charges come from atoms. Usually they're not floating around in space, although they can. When you have something that's equal amount of protons and electrons, that's electrically neutral. And then when you have different numbers of protons and electrons, that becomes charged. And to find the net charge, we multiply by Q, and to find total number of charges, we divide by Q. So in the next video, you'll learn about the interaction of charge, how charge repel and attract, the conditions for that, how to make something charged now, because I didn't tell you how to charge things at all, I just said they were. Now I'm going to teach you how to charge something, and it's based on the type of material it's made out of. And then lastly, we'll talk about the force of the charge, the real physics behind it, how much push do you get from charges. And they're actually a very strong force, and we'll talk about all that fun stuff in the next video. Bye-bye.